In 1804, in a workshop in Lyon, France, a silk weaver named Joseph-Marie Jacquard built a loom that could read. It took instructions from cards punched with holes. Hole here, no hole there, and the loom would raise or lower threads to weave a pattern automatically. It sounds humble, but something profound had just happened. A piece of information, an idea for a pattern encoded in cardboard, was now controlling a machine. Thought had been separated from the thinker. You could hold a program in your hand. A few decades later in England, Charles Babbage saw those punch cards and had a bigger idea. If cards could tell a loom what to weave, cards could tell a machine what to compute. His analytical engine, designed in the 1830s, was a general-purpose computer made of brass gears 100 years before electronics. It was never finished, but his collaborator, Ada Lovelace, understood what it meant better than anyone alive. She wrote that such a machine could manipulate not just numbers, but anything that could be represented by symbols, even music. Meanwhile, another Englishman was doing something that seemed completely unrelated. George Boole, a self-taught mathematician, published a book in 1854 arguing that human logic, the actual laws of thought, could be written as algebra. True and false became 1 and 0. And, or, not became operations like addition. Reasoning itself reduced to arithmetic. It was beautiful. It was also, for 80 years, basically useless, a curiosity for philosophers. Then, in 1937, a 21-year-old graduate student named Claude Shannon wrote what may be the most important master's thesis ever written. Shannon had spent a summer working with telephone switching circuits, physical relays that click, open and closed. And he noticed something. A switch is either on or off, 1 or 0, true or false. Boole's algebra of thought and the behavior of electrical circuits were the same mathematics. Stop and appreciate what that means. Before Shannon, logic was something that happened in minds or on paper, slowly. After Shannon, logic could happen in metal and electricity, and once thinking becomes physical, it inherits the properties of physics. Electricity moves at nearly the speed of light. It never gets tired, never gets bored, never makes a careless slip. Any logical operation you could write on paper could now be executed millions, then billions, then trillions of times per second. Shannon didn't make machines smarter. He made thought fast. That's the hinge the whole modern world swings on. But there's another mathematical thread running through this story, and it starts even earlier with Newton and Leibniz and the invention of calculus in the 1600s. Calculus, at its heart, answers one question: how do things change? If you nudge this, how much does that move? That sounds abstract until you realize it's the mathematics of improvement. Because if you know which direction makes something better, you can take a step that way, and another, and another. Hold that thought, because it becomes the secret engine of modern AI. Through the 20th century, the pieces assembled. Alan Turing proved that a simple machine reading symbols off a tape could, in principle, compute anything computable, and then asked plainly whether machines could think. In 1956, researchers gathered at Dartmouth College and gave the field its name, artificial intelligence. Early efforts tried to handwrite the rules of thought, if this, then that, and hit a wall. It turns out humans know vastly more than we can explain. Nobody can write down the rules for recognizing a face. The field crashed into disappointment so severe, they're called AI winters. If you enjoy these videos, do check out our mobile app. Treehorn makes audio shows like this every morning. We also cover tech news, politics, entertainment, and more. Treehorn is available on both iPhone and Android. The answer, when it came, flipped the whole approach. Don't teach the machine rules, build a machine that learns its own. The seed was planted early. In 1958, Frank Rosenblatt built the perceptron, a simple brain-inspired model that could learn to classify basic patterns by adjusting its internal settings called weights. It was crude, and in 1969, Marvin Minsky and Seymour Papert published a critique showing just how limited it was. The field mostly walked away, but the perceptron had introduced the idea that would eventually win. Intelligence would not be programmed, it would be learned. But learning poses a thorny problem, one that grows with scale. A modern neural network is the perceptron idea expanded into an enormous web of simple connections. Each connection has a numerical strength, a dial, billions of them. Set them right, and the network recognizes faces, translates languages, writes essays. But how do you set billions of dials? You can't do it by hand. You can't reason your way to the right values. You need a procedure. This is where we return to calculus. Show the network an example and let it guess. Measure how wrong it was. Then calculus asks of every dial, if I turn you slightly, does the error rise or fall? And by how much? Turn every dial slightly toward lower error. Repeat the process across enough examples, and those tuned numbers come to represent deep understanding of the features of reality. For decades, researchers refined the mathematics and kept puttering around with neural networks, but the networks were far too small to produce impressive results. The idea was waiting for data and computing power to catch up. Then came internet-scale datasets and graphics chips capable of adjusting millions of weights in parallel. In 2012, Alex Krzyzewski, Ilya Sutskever, and Hinton used both to build AlexNet, which demolished the leading image recognition competition. Neural networks moved from the academic fringe to the center of artificial intelligence almost overnight. This brings us to OpenAI, born partly from one of Silicon Valley's infamous middle-aged man relationships. According to Musk, he and Google's Larry Page were once close enough that Musk regularly had sleepovers at Larry's house when work brought him north to Tesla's Fremont factory. But their late-night conversations about AI exposed a split. Page saw machine intelligence as humanity's possible successor, the child surpassing its parent. Musk believed who knows what. Page called him speciesist. Their friendship dissolved, and Musk increasingly felt like Google needed a counterweight. Nick Bostrom's 2014 book, Superintelligence, was the talk of the town at the time. AI was on the mind of many insiders. Musk famously started saying that creating AI was like summoning the demon. Sam Altman, then president of Y Combinator, had machinations of his own, a new AI research org. No doubt ideas like this were swirling around private dinners. In 2015, Altman approached Musk with a proposal for a non-profit AI lab that could develop the technology outside Google. The early days involved a lot of wandering with unclear payoff. The lab tried many directions: video games, robots trained in simulation, agents that learned through self-play, even a bot that battled professionals in Dota 2. Then came Alec Radford, a household name, assuming you're a giant nerd. In 2017, he trained a neural network on tens of millions of Amazon reviews. Its task was almost comically basic: predict the next character. Nobody taught it which reviews were positive or negative. But inside the trained network, one neuron had become a remarkably clean sentiment meter. The lab lent in, following the clue. Meanwhile, a young researcher named Dmitry Bogdanov had a stroke of genius. Working on machine translation, he remembered learning English in school. A translator doesn't look at the original sentence once and then work from memory. Their eyes keep moving back across it, finding the words that matter for each new word they write. Why not let the network do the same? In 2017, 8 Google researchers took the idea further. What if attention wasn't merely bolted on to the old machinery? What if attention was the machinery? Their paper, Attention is All You Need, introduced the transformer. Words could weigh their relationships to other words directly, with many calculations happening in parallel. The design fit modern chips beautifully, allowing language models to absorb more data and grow much larger. OpenAI's Ilya Sutskever immediately saw what it could become and urged Radford to pursue it. In 2018, Radford and his colleagues combined the transformer with the lesson of the sentiment neuron. Predict enough language and useful knowledge may emerge. They called it a generatively pre-trained transformer, GPT. GPT-2 became more fluent. GPT-3 became startlingly flexible. Reinforcement learning with human feedback tuned those weights into a helpful, conversational personality. ChatGPT was born. Notice what is driving all this. Not a plan, not a command from a dear leader. Nobody charted a course from Jacquard's Loom to ChatGPT. Economic and status incentives gathered behind every obstacle until those obstacles fell. The curious pressed for more, the ambitious want to be first. Companies and nations feel they cannot afford to fall behind. Nobody directs the process, but everyone keeps it moving. So where's all this going? Nobody really knows. It's not even clear how smart anything can get in the universe. The human brain is one biological solution, but it has obvious limits. No one can give birth to a galaxy brain, and for most of our history there was barely enough food to power the regular kind. Machines face different limits. They can be placed in ever larger buildings and power plants. The gap between us and other animals produced mathematics, cities, and spacecraft. What will the gap above us produce? It's a provocative question. Anywho, I'm tired now, and the video is over. It's a special time to be alive, comrades. Are we going to sci-fi land? Nobody consulted me rudely. Well, at least we're going together. Until next time.